In this video, we're going to discover an upper bound on the number of edges in a planar graph or a planar bipartite graph. So first, we're going to assume that you have a planar graph with the property that every face of a drawing of G has a triangle as its boundary. So for example, this graph down here has 6 vertices, and you see there are 8 triangles, including the outer face, which is also bounded by a triangle, and it has 12 edges. A fact we're going to claim is that if you double the number of edges, you get 3 times the number of faces. So the way to prove this is to count the number of pairs consisting of an edge and a face containing that edge on its boundary. And one of the things you can notice is that every edge has to bound at least 2 faces, no matter what. Because if you take the interior of an edge and draw a circle around it, it can only have 2 regions, one at most. So this is ignoring cases like a tree where both regions are actually part of the same outer face. So we're saying at most 2. On the other hand, since every face is bounded by a triangle, given any one of these faces, there are exactly 3 edges on its boundary. So if you multiply the number of faces by 3, you count the number of these pairs. If you multiply the number of edges by 2, you also count the same number of pairs. Technically, this is an inequality, but in our case, we're making an equality because the point is if you had one of these weird cases with an edge bounding exactly one face, then you would just add more edges to your graph while maintaining this property. And that would actually force the equality. In red, I have a similar fact. If every face of a drawing of G was bounded by a quadrilateral, then every face has 4 edges on its boundary, so our equality gets replaced. It's no longer 2e equals 3f, but 2e equals 4f. And the example I drew is the edges of a cube. So there are 6 faces, 12 edges, and 8 vertices. And you do see that if I multiply 12 by 2, I get 4 times 6. Similarly, with my original graph for the triangles, if I multiply 8 by 3, I get 12 times 2. So now let's take this equality and see what we can do with it. We know Euler's formula is that the number of vertices minus the number of edges plus the number of faces is equal to 2. And so if I rearrange terms, I see that the number of edges is the number of vertices plus the number of faces minus 2. And since 3 times the number of faces is twice the number of edges, I can replace with f with 2/3 the number of edges. And so now I have e on both sides. So if I subtract the e and isolate it on one side, I get 1/3 the number of edges is equal to the number of vertices minus 2. If I multiply both sides by 3, I see that the number of edges in a plane graph where every face is bounded by a triangle is 3 times the number of vertices minus 6. So in these special types of planar graphs, the number of edges depends entirely on the number of vertices. Similarly, if I look at the plane drawing where every face is bounded by a quadrilateral and I do the exact same calculations, I discover that the number of edges is twice the number of vertices minus 4. So what can we get from this previous fact? Well, we discovered the following proposition. For a connected planar graph, the number of edges is bounded above by 3 times the number of vertices minus 6. On the other hand, for a bipartite planar graph, the number of edges is at most twice the number of vertices minus 4. And the proof for the first case is just keep adding edges to G while making sure it stays planar. So in the worst case scenario, I take this graph and I keep adding edges. If I can't add edges anymore, it turns out it must be because every face is bounded by a triangle. And the point is, if you had a face with a degree 1 vertex in its boundary, I just add an edge to any other vertex on the face and create a cycle. And in general, if I have some sort of larger polygon on a face, I could just add a chord. And either way, I've added more edges while maintaining the planarity of the drawing. And therefore, if I can't add anymore, it's because I have only triangles on every face. At that point, the number of edges is exactly this formula we had before. But since we added edges to our graph, this creates an upper bound for the number of edges in the original graph. So the number of edges is at most 3 times the number of vertices minus 6. There is a second part of this proof. If G is bipartite and we want to maintain keeping it planar and bipartite, then you have this feature that for every cycle, because it's bipartite, the number of edges on the cycle must be even. So then instead of taking a chord, you take a chord that skips 2 vertices to maintain the bipartiteness. So this forces the property that every face is bounded by a quadrilateral. So then we have our other bound coming from that type of plane drawing. So as a corollary of this result, we can look at K5. If you count the number of vertices, there's 5. If we look at our formula, we see the most number of edges in a planar graph on 5 vertices is 9, but K5 has 10 edges. So this tells us that K5 is not planar. And similarly, larger complete graphs also cannot be planar for the same reasons. Similarly, if you look at the complete bipartite graph K33, that is bipartite, so the number of vertices is 6. According to our formula, there can be 8 edges at most if it's planar, but it has 9 edges, and therefore K33 is also not planar. So this tells us our 2 favorite types of complete multipartite graphs are not planar. In general, this approach doesn't always work, because as we'll see in a later lecture, the Peterson graph is not planar. But if you do this calculation, you discover that the number of edges of the planar of the Peterson graph is actually smaller than the upper bound on the number of edges in a planar graph on 10 vertices. Therefore, this upper bound is useful for showing that a graph is not planar, but it doesn't always work. However, for a future lecture, I do need to note that another feature you get from our upper bound is that every planar graph has a vertex of degree at most 5. And the proof of this is to suppose that the degree of every vertex is at least 6, then twice the number of edges, as we've seen before by the handshake lemma, is the sum of the degrees. Since each degree is at least 6, that's at most, or at least 6 times the number of vertices. If I divide through by 2, this tells me that the number of edges is at least 3 times the number of vertices, but since we're assuming we have a planar graph, this contradicts our upper bound, so it's a contradiction. Therefore, every planar graph has to have a vertex of degree smaller than 6.